Hi guys. I know you want some Lego, and there will be some Lego, don't worry about that. And we are going to go through the entire history of the universe, all right? But that's only in the second half of the talk. The first half of the talk, we need to actually think about the rules that we need to build a universe. So we're going to start with a disclaimer. Now, my disclaimer is that, of course, I am in no way telling you that these little blocks are anything like actual particles. It's just an analogy, okay? Because we know that actually these are made of trillions and trillions of different particles, and they form molecules and atoms and everything else. But an analogy is a really important and really interesting thing to use in our day-to-day explanation of science. Because really, if we think about it at its heart, all our scientific theories are nothing but an analogy of nature. Because they are not nature itself, but they are essentially written in the language of mathematics, the most accurate analogy that we can actually find to describe nature. And for those of you who like Venn diagrams, here's one coming up. So you can imagine nature as being this massive expanse that we are, as scientists, trying to understand. And we've got current scientific theories, which we know doesn't explain all of nature. For instance, there are known unknowns, like dark matter and dark energy, but there are obviously unknown unknowns as well out there. So we know that our scientific theories don't cover all of nature at all, but we know we're getting closer and closer to understanding more of it. And as a teacher, when I'm teaching in a classroom, I use everyday analogies to teach these scientific theories. And I think it's a really important thing to be able to use everyday analogies to try and learn about scientific theories. Because if we can actually find a way of hooking into something, then we can understand something more complex. So this is my disclaimer for using Lego. And at the boundary between everyday analogies and the scientific theory is the understanding of what the scientific theory is at a deeper level. And if we can understand where everyday analogies, like Lego bricks, break down, and we can understand where the scientific theory takes over, we learn more about the scientific theory. And really, that is hopefully going to be teaching the next generation of researchers then, where they will be working at the edge of scientific theory and trying to push into the boundaries of nature, exactly how they might press forward by critically analyzing and asking questions of the current best analogy of nature, which is the scientific theory they understand. I hope I've convinced you now. Let's go on to the Lego. So as a particle physicist, I'm very much interested in the idea of atomism, the idea that if we can break down the universe into its smallest building blocks, we can then try and figure out how to build those up into pretty much everything around us. We know that the atom itself is made up of smaller things. The atom is actually made up of a central nucleus, and around that we have electrons. Now, we know that nucleus is also made of smaller things. The nucleus is made of protons and neutrons. You may not know that we know the protons and neutrons are also made of yet smaller things. They are made of particles called quarks. Now, the word quark doesn't really mean anything. It's just the sound that Murray Gell-Mann, the person who named the quark, had in his mind. But he found that name in James Joyce's Finnegan's Wake, and it comes from the sentence, 3 quarks for muster marks. And so, really, this is where the idea of atomism ends, because we get to this point where we find ourselves with building blocks that we don't seem to be able to break apart. Now, this might not be the end, but right now, this is where we're at, that the quarks and electrons are what we call fundamental particles, things which seem to be indivisible, no matter how hard we hit them. And in fact, if we boil down our universe into the most basic building blocks it's made from, 99.9% of our universe is actually only made from 3 building blocks. Okay? It's not the neutron, the proton, and the electron, but it is the up quark at the top here, the down quark, and then the electron. Now, there's the neutrino here, and I spent 8 years as a neutrino physicist. You'll be surprised to know that I'm not going to talk too much about neutrinos today, but I will mention it in a second. But these three basically make up all of the atoms, all of the 99.9% of the universe we live in. The up and down quark, as we'll discover in a second, combine to make protons and neutrons. And the electron is responsible for chemistry and electricity and things like that. Now, we don't know why. We've got no clue, but nature, in its infinite wisdom, has chosen to copy these first few particles twice over. Now, these copies are identical in every way in which they interact with each other. The only difference is that they are more massive. They have a greater mass, which in particle physics language just means they're unstable. Because if you have a lot of mass and there's a way of getting to a lighter mass, then you'll take it. And that's why most of these heavier particles don't really exist day to day, and that's why 99% of the universe is basically those first few particles. Now, these particles make up the matter around us. They construct together. They're things called fermions, and they build up into structure. And so alongside these, we have building blocks which communicate between these building blocks. So these things are called bosons, and they carry the fundamental forces of nature. I'm going to talk a lot more about these, but we have things called gluons, which glue the quarks together into particles. You'll notice there's no mistake that these have a color, and so do the gluons, and we'll talk about that in a second. Then there is something called the photon, which, well, you should be aware of because billions of them are streaming into your eye now every single second. The photon is the particle that exchanges the electromagnetic interaction, and it interacts with everything that has an electric charge. And then there is something called the weak bosons. Now, the weak interaction we're going to touch upon, but it's rather strange. It doesn't actually impose forces on particles. It's more of a transformative interaction. And it can actually change up quarks into down quarks and vice versa. And we'll talk about that in a bit. Then there is something called the Higgs boson. Now, the Higgs boson, if you've got questions about the Higgs, we'll go through them. But I'm just going to leave off with saying that the Higgs boson is the thing which gives a mass to some of these particles. Without the Higgs boson, essentially these particles don't weigh anything. They don't have any mass at all. And along with the building blocks, the fermions, and the bosons, which are the exchange particles, this is all known as the standard model of particle physics. And it's a hell of a lot more simple than the periodic table with 118 elements. But remember, the periodic table is made of just these three particles, all 118 elements, made from just those three blocks. So we're actually describing a hell of a lot more than just the chemicals that exist on Earth. So I'm going to talk now a little bit about the forces of nature. So gravity doesn't really come into play when we're talking about particle physics. Simply, the particles are too light. They have too small a mass. So we're going to skip right over that. We're going to talk about electromagnetism. That's quite interesting. Now, electromagnetism, like gravity, has an infinite range, which means that a charged particle on Pluto would feel, albeit a very weak attraction to a charged particle on Earth, because they would exchange photons between themselves. The electromagnetic force is a lot stronger than gravity, and so we do actually care about it when we think about the particles with electric charge. Then there are two other interactions. I mentioned them briefly. This weak interaction is responsible for things like the beta decay, radioactive decay, and transformations like that, which we'll talk about in a second. But it's limited to within the range of the nucleus. It can't actually really influence anything outside of that. And then there is this strong interaction. The strong interaction is the thing which keeps quarks bound together to form protons and neutrons. And the range of that is even smaller. It's really only limited to the size of a proton or a neutron. Now, the way in which these interactions actually impose themselves on the particles is because these particles have certain properties. And the property that we say these particles have is called charge. Now, everyone's familiar, I hope, with electric charge, the idea that certain particles will be either positive or negatively charged and will be more or less positively charged than each other. And anything with an electric charge, so the quarks and these particles here, the electron and its heavier versions, they all have an electric charge and so can interact via the electromagnetic force. But the poor neutrinos at the bottom don't. So we can forget those for this particular force. And I hope you're all familiar with the fact that positive and negative charges want to attract each other. Just as a quick example, and the reason for this is that essentially if something is electrically neutral, or neutral in terms of any charge, it's much more stable. So I've got just a quick demonstration here where I'm going to build up some charge in these opposite sides of this device. It's called, does anyone know? It's called a Wilmshurst machine. And what I'm going to do, I'm going to build up charge in both of these, and it's going to be positive in one and negative in the other. And watch what happens. Can we have the lights down for a second? So the friction between the brushes will exchange electrons. And eventually, if we build up enough charge, we should get some electric sparks going off. Bear with me. This is going to be underwhelming now. But we should get, there we go, we've got some nice sparks going. And the reason we get some sparks is that there is so much of an energy divide between the two different charges, thank you, that eventually that energy causes the air to break down, and the otherwise electrically neutral atoms get ionized. So the electrons literally get ripped out of the atoms in the air and allow an electric current to flow between the two. And the reason that charges don't like being separated is because they have an attractive force pulling them together. And the reason they have an attractive force pulling them together is actually because they know if they get together, they're lower in energy. Now, positive and negative charges attract one another and come together simply because you can think of them falling down an energy well. Because that's pretty much what's happening, is that the energy between them is much lower than when they are separated. And that is the reason behind the force which pulls the two charges together. And when they come together to form something that's electrically neutral, then that is much more stable than when they are separate charges apart. And the universe just wants to be in its lowest energy state it can be in. And not only do we have building blocks, but we also have anti-building blocks. So I'm going to touch on this briefly, but essentially, we've got these 12 building blocks of nature, and if we mirror these building blocks, in other words, if we change things like the electric charge that each of the blocks have, we create something called antimatter. And the antimatter is the total opposite, apart from they have the same mass. And so the first antimatter particle to have been discovered was the anti-version of the electron, called the positron. And you'll notice the electron has what we call negative electric charge, and the positron has a positive electric charge. And so in discovering antimatter in 1932, we essentially doubled the number of particles that we have in our remit to be able to build something. But the only problem is, when antiparticles meet particles, they annihilate. And so really, they're not very good for building a universe within our matter-dominated universe. So the up quark has a positive 2/3 electric charge, the down a negative 1/3, the electron negative 1, and if you look, their antimatter versions are totally the opposite. And if you make it opposite charge, then they interact via the interactions in totally the opposite way. It gets a bit more complicated when we think about the other interactions. So when we're talking about electric charge, that really is just an analogy. There's no deeper meaning to thinking that something is positive or negative. And it was Benjamin Franklin that first assigned the symbols positive and negative to charges. As a polymath, he found it much easier to deal with numbers than to keep talking about resonance and vitreous electricity, which were the two types of electricity talked about until that point. He was the person who defined positive and negative. So if you're learning electricity in school and you're complaining about the fact that conventional current goes positive to negative, you can kind of blame Benjamin Franklin for that. But the strong interaction is a little different. We can't just have positive and negative charges. It's quite a bit more complicated. Because unlike positive and negative charges, which can all be drawn on a one-dimensional number line, the strong interaction actually has more than one charge. It doesn't have one, two, but it has three charges. Now, this is a bit more complicated, and so we need to think of a different analogy. We can't just use the positive and negative that Benjamin Franklin first imposed. And the idea was to use color. A little bit of a biology segue, and I am paranoid because I know there are biologists in the room. We're going to talk a little bit about the eye, because the eye really underpins the analogy here. So at the back of our eye, we have rods and cones, two types of different cell which detect the light that we see. The cones are the ones which give us our color information, and there are three different types of cones. Essentially, these different types of cones are sensitive to different regions of the electromagnetic spectrum, or what we would say are different colors. We have cones which are predominantly sensitive to blue light, cones predominantly sensitive to green, and cones that are sensitive to red. And from these three different cells, we build up our picture of the world around us. So any color that we see is just a combination of these different cones triggering. So we see our entire world really not as a spectrum of colors, but in red, green, and blue to different amounts. And this is why the screens around the room actually, and the TVs you've got at home, use LEDs, which only really flash red, green, and blue to different amounts. But from that, they can build up the entire spectrum of colors. And so I'm going to actually show you a live demonstration, so I don't need to actually do this for sure. But the three primary colors are the colors that are used for these strong charges. So if I can have the lights down. Cheers. Thank you. So here we just have three different LEDs, a red, a green, and a blue LED. And in the center, I hope you're all agreeing, what color is the light? White, right? And so if all of those cones in our eye are being triggered, then what we see is something that is white. And would you describe white as a color? Yeah, kind of. In this analogy, please say no. Because essentially, when the three colors come together to form white light, we can say that they have no overall color anymore. They are colorless. Now, this central point where it's white light is the idea of neutrality in terms of this strong charge. So where positive and negative and electric charge come together to form zero, numbers are nice and easy to deal with, here, the colors, when all three primary colors come together, they form something which is pure white light. Now, on the overlaps, you'll notice there are some secondary colors. So opposite green, we have opposite green, we have magenta, opposite red, we have cyan, and opposite blue, we have yellow. We'll talk about those in a second. So if you want to form something which is color neutral, then you need at least three things with charge to come together. So if you could turn the light up. Thank you. Right, so I'm going to skip over this video, we don't need this. So the idea of what we would have as our positive and negative has changed to being color axes. So the idea is that these three different possible charges are just represented by the primary colors of light. So we have a green axis, a blue axis, and a red axis, which we would kind of otherwise think of as being maybe positive, okay? And when we have all three primary colors, they form something which is neutral in charge. And so we can create these by bringing together three quarks. You bring three quarks together, each of them with a different primary color of light, and what they will form is they will form something which is colorless. We can bring together two up quarks and a down quark to form a proton, or we can bring together two down quarks and an up quark to form a neutron. And once the quarks have combined, they form something which is color neutral, and that's actually lower in energy. And so they're happy, and they stay like that. And so these particles no longer have any color, and so no longer attract other quarks towards them. So we can think of the positive side of our axes as being the primary colors of light. But now we've got to think about, well, what do we mean by the negative, or anti-colors, or the opposite? Well, I mentioned the secondary colors, and that's where we're going next, because the secondary colors can be thought of as the total opposite of the primary colors, in a way, okay? So for instance, magenta can be thought of as the opposite of green, because magenta is everything that green is not. It's just a mixture of red and blue. And cyan is everything that red is not, and so on, okay? Just to try and prove this to you, please stare at the cross in the center. Put your hand up if you see a green circle moving around, okay? Right, now, keep your hands up and start following the green circle and put your hand down if it disappears. Right, there's always a few people who don't quite see it disappear, But I hope you can see that actually the green circle isn't actually there. What is there is an absence of magenta. So if you take away magenta, your brain fills in green. So if we're talking about the color analogy being how we see color, I hope you're now convinced that the opposite to magenta is green and vice versa. It doesn't work quite as well with blue and yellow or red and cyan. Does anyone know why? So the clue is that magenta is not actually on the rainbow. Magenta is a color that is entirely made up by your brain. And so it's much easier to see a difference between a real color and a made-up color. It's really because green here in the middle of the rainbow is obviously going to trigger those green cones. But if you don't have any green light triggering those green cones, and you have red cones and blue cones being triggered, what color do you say it is? Well, your brain makes up magenta. And so it works really well with green and magenta simply because they are really opposite in terms of how we see the world. But what happens is if we bring together these three secondary colors, you can also make pure white light. Or in our analogy, this means we can make totally color-neutral particles. Now, bringing together the three secondary colors is the same as bringing together three antimatter versions of quarks, because when we mirror matter to antimatter, we change everything about the charges, everything about the way in which they interact with the world around them. And so the secondary colors can be thought of as anticolors, or the colors of our antiquarks. Mixing them together makes colorless particles again. And so we can create antibaryons or antiprotons or antineutrons. There is another way, and I'm sure some of you in the audience have noticed this. If we mix a secondary color and a primary color, we can also create something which doesn't have a color anymore. So if we mix blue and its opposite number yellow, or we mix red and its opposite number cyan, or green and magenta, then we also create something which is colorless. But I mentioned earlier that matter and antimatter, in this case quarks and antiquarks, don't really like to sit together. And so this form of matter is only metastable. It doesn't like to exist for very long. But these things are called mesons. And the lightest mesons with electric charge are called pions. And we can create these pions by adding an up quark and an anti-down quark, or a down quark and an anti-up quark together. And again, they form particles which are low in energy because they have no overall color charge. Now, I mentioned I would briefly touch upon the weak interaction, and this is it. And don't worry, this is the last bit of physics before we go through the history of the universe. So, beta decay occurs in the nucleus of really heavy elements. Actually, not just really heavy elements, also element 43, technetium as well. But and what happens is essentially our neutrons, which are two downs and an up, turn into protons. And in the process, in the transformation, electrons are seen to be emitted. And when these electrons were measured, they were expected to have the same energy, because using Einstein's most famous equation, the energy from the electrons would come from the difference in mass between the proton and the neutron. And because it was only really the electron that was being fired out and the nucleus recoiling, it was thought that these electrons would have the same energy each time, because they would have to conserve the energy that they were taking away, the momentum they were taking away. And so it was thought these electrons, if we measured them time and time again, we should always see that they have the same energy, and that energy was equal to the mass difference between proton and neutron. But what was actually seen was that these electrons were coming off with a whole spectrum of energies, which was a problem. Either the conservation of energy was being violated, or there was something else going on. And that led to the prediction of the neutrino. Now, the neutrino particle, if it's a third candidate that slips away unseen, can take away any share it wants of the momentum. And so that would be the reason then that the electron would have differing values of energy. And for those of you who like Feynman diagrams, especially Lego Feynman diagrams, this is the process as it's happened. We know now that actually what's happening is a neutron is emitting a weak boson, and that weak boson goes on to decay and form an electron and an anti-neutrino. And essentially, the take-home is that the weak force is great because it allows us to turn particles into one another. So the up quark can turn to the down quark and vice versa. This is important because if we want to actually decay, if we want to become something lighter, or indeed if we want to become something heavier, we need the ability to be able to transform, and that's what the weak interaction allows us. So, universe construction rules. The strong force basically makes particles that have no overall color, so it brings quarks together either into groups of 3, which we call baryons, or a quark and an antiquark to form a meson. The electromagnetic force brings positive and negative electric charges together to form things which are electrically neutral. And the weak force is there as basically an assistant to allow particles to change if they need to, if it allows them to get to a lower energy. These, along with the building blocks, are all we need to build a universe. So, let's do it. Okay, right? And you thought this would be the beginning of the talk. We're going to build this universe. This is the Hubble Deep Space Field View, and essentially Hubble just looked into what they thought was a dark patch of sky for many days on end, and actually saw galaxies as far away as 13 billion light years. So the universe is a rich tapestry, but it's all made from matter, and so that's all we're going to focus on right now. This is a brief history of our universe in LEGO. It's very, very biased towards particle physics. I mean, the halfway line here is just 10 seconds after the Big Bang. Then we get to 380,000 years, and then that's all astrophysics. We're not really interested. We're going to focus on this early stage, and we're going to go through the entire history of the universe. So we're going to start from the Big Bang. And after the Big Bang exploded forth with immeasurable amounts of energy, lots of that energy got transferred into the mass of new particles, using Einstein's famous equation, E equals mc squared. And these particles essentially formed a very hot, dense, thick soup in the early universe. And the early universe was very, very small. We're talking about much smaller than a golf ball. And at this stage, essentially all of these particles were free from one another. They had so much energy that despite the forces of attraction and things like this, they were able to overcome them because they were moving so fast. But it wasn't very long before that strong interaction took hold, and it caused the quarks to form particles like protons and neutrons. And in the first few moments, the first protons were formed, and forevermore, quarks would be locked up into these particles. And so after the first second, the universe was no longer a mess of quarks and electrons and things. It was a mixture of just protons, electrons, and a few neutrons. But again, as we've learned from beta decay, they're not perfectly stable. And then in the very first minute, the universe was really hot and dense. It was so hot and dense that these protons slammed into one another, some of them transforming into neutrons, and about 25% of the universe got turned into helium-4. So these protons and neutrons were slamming into each other with such force that the strong interaction actually stuck them together. And in the first minute, the universe looked a little bit different. So we had lots of protons, a few neutrons, electrons, and then some of these helium nuclei around. 380,000 years later, the universe had expanded a lot. It had cooled down a lot. Deep space was about 1,000 times hotter than it is today. And at that temperature, the electrons could no longer overcome their attraction to the protons that had a positive charge, or the helium nuclei that also had a positive charge. And at this point, what happened was, for the first time, the electrons combined with the proton to form hydrogen atoms, and with the helium nuclei to form helium gas. And at this point, the universe went from being electrically charged to electrically neutral. And so before this point, light had been bouncing around between all these electrically charged particles. But after this point, the light that was bouncing around was free to move out into the universe. And in fact, that is around us today. That is what makes up about 5% of that fuzzy static in between channels when you haven't got your TV tuned properly. It's something called the cosmic microwave background. So next time you see an untuned channel, remember 5% of that is from 380,000 years after the Big Bang. The universe then was electrically neutral, but there were big clouds of gas growing. These clouds of gas got to hundreds of thousands of light years in size. And once they got that large, with so much mass, then gravity, the weakest of all forces, started to take hold. So the gas over this side attracted the gas over this side of the cloud. Gas up here attracted the gas down here. And the eventual result was that all of the gas started collapsing inwards. As it collapsed inwards, those of you who are studying your GCSEs, gravitational potential energy turned into kinetic energy. That kinetic energy became thermal. All of that heated up. The gas heated up so much that the electrons were able to liberate themselves from the protons and helium nuclei again. And that formed a plasma. But it didn't stop there. They fell inwards even more, losing more gravitational potential energy and turning it into kinetic, until it heated up so much that at the very center of some of these balls of gas was a temperature that hadn't been seen since the first minute after the Big Bang. And if you remember what happened there, those protons and neutrons had such an energy that they could collide into each other and fuse together to form helium. And that's what happened. And as they did so, they emitted light. And so, essentially, what was happening in the early universe was going on now in microclusters all around the universe, but in much smaller amounts. And this is essentially what's happening in our sun right now, is the hydrogen is being stuck together to form helium. And so it's emitting lots and lots of light. And as it emits the light, that light is trying to make its way out of the sun. But because it's trying to push its way out of a plasma of electrically charged particles, essentially it gets slowed down. And it can take thousands of years for light to move from the center of the sun out to the edge. But then it's 8 minutes to Earth. But that pressure, as the light tries to push its way out, is the thing which helps the sun fight back against gravity pulling inwards. And this is where our sun is right now. It's in a stable location. So it's producing enough light to fight back against the gravity pulling inwards. And it's in a stage of its life called the main sequence. And in its main sequence, it is creating lots of helium to try and fight back against gravity. But eventually, the sun will lose. Because eventually, it will have used up so much of the protons in its central core that it will not be able to create more helium and therefore more light. And so it will stop being able to push back and it will collapse once more. When it collapses, that energy gets turned into thermal energy again, which means that the now very rich helium core gets boosted in its temperature, which means the helium can whiz around fast until they collide together to stick together. And then helium can stick together to form heavier things. It can form beryllium-8. Beryllium-8 is very unstable and actually collapses back into helium-4 quite quickly. So it's a pretty useless way to go. But in its short lifetime, if a helium-4 collides into a beryllium-8, we actually form something which is useful. We form carbon-12. And so we kind of leapfrog all of the elements between helium to carbon because the next most stable nucleus that is formed via this process of sticking protons and neutrons together is carbon-12. And so what will happen to our sun is it will collapse, but then as soon as it's able to turn helium into carbon-12, it will produce lots more energy in the core. Not only that, the entire sun would have heated up, so that also around the center of the sun will be an envelope of particles, so those helium, those protons that otherwise were too low in energy to stick together. Those protons would have heated up and they can now collide to one another and stick together to form helium. So now not only can the sun produce energy by sticking helium together, it can also produce energy by sticking more of the protons together around the outside. So it's got two forms of creating light, which means that it can actually push back against gravity with a much greater force, which will cause our sun to swell in size, and it will form something called a red giant. And when our sun does this in about 7 billion years, estimates range between 5 and 7 billion years, essentially it will engulf Mercury and Venus. It will certainly blast all of the atmosphere off the Earth and probably turn the Earth back into a molten ball of rock. But as I say, it's about 7 billion years away, so I wouldn't worry too much. Stars that are larger than the sun will continue this process. Once they've used up the helium in the center, they will collapse a little bit, heat up some more, find a new way of creating energy, and push back again with even greater force against gravity and grow in size. And essentially, it does this by adding more of those helium to the carbon-12. If we add a helium to carbon-12, we form oxygen-16, another essential molecule for essential atom for life. If we add another one, we form neon-20. Adding another, we form magnesium-24. And we keep stacking on one after the other until we get to the point where we reach something that is stable. We reach something called iron-56. Now, iron-56 is the most stable naturally occurring nucleus. Once you've reached iron-56, you're in a bit of trouble because trying to stick something to iron-56 doesn't release light. Up until that point, you've been creating lots of light by sticking these things together. But with iron-56, no more light can be produced. In fact, you have to put energy in. You'd have to use up some of that light to stick something to iron-56. And a star isn't in the business of using energy. It's in the business of making energy to fight against gravity. And so once we reach iron-56, that is essentially the end of the star's life. Because the star can no longer actually sustain itself against the inward pull of gravity. And eventually gravity wins. And the most massive of stars will end their lives in something called a supernova. Everything collapses inwards and bounces off. And in a briefest moment, there is a flash of light which outshines every other star within the galaxy that this star is within. And then that's the end of its life. But in this supernova, there is a positive outcome. The extra energy from the collapse goes into pumping up these nuclei to extra size. As mentioned, you need extra energy to put more protons and neutrons onto iron-56, and that's what the supernova provides. As it collapses, it pumps up these nuclei to heavier and heavier elements, and that's where we end up with a great number of the elements heavier than iron. There are other kind of exotic ways in which you can get to heavier elements as well. But the elements of the periodic table are made up mainly, as you can see, we mentioned the blue here, Big Bang fusion, the hydrogen and the helium, predominantly made in those first minutes, right? So the protons and the helium nuclei made in the first minutes in what we call Big Bang fusion. Then the elements between helium and carbon are kind of made by breaking apart heavier things. And cosmic rays, high-energy particles, which are raining down upon us now, actually break up some of those nuclei to create boron and beryllium. And that's the reason they're so toxic to life, is because they're not really found very prevalently. They're only created when other things are broken up. Then we have the exploding massive stars, so the death of stars spreading forth all of these elements into the universe. And in fact, that's why we know that our sun must be a second-generation star, because otherwise the elements that make up the planet wouldn't have existed to actually make the Earth and you and me. And so the sun is actually occupying a region of space that was occupied previously by one of these supermassive stars. And then there are some other exotic things, which I'm not going to talk about now, but there are other ways in which you create the heavier elements, which are a bit more kind of involved than just these fusion processes. And essentially, once you've got the chemical elements, that's all you need, right? That's a universe. Well, as a particle physicist, that's what I feel. That's where I'm going to leave it. But I just want to mention that I kind of jumped over that very first slither of time after the Big Bang. I kind of left a horizon. I said straight away, Big Bang energy, whoop, we've got some building blocks, right? I missed out this bit. And the reason I missed out this bit is because right now we don't actually know what happened very close to the Big Bang, or indeed at the Big Bang. We are quite aware of the evolution of the universe from a tiny fraction of a second after the Big Bang, but we're not sure how these building blocks actually came to be in the first place. There are many theories, and those theories are being tested every single day at the Large Hadron Collider, also in neutrino experiments such as IceCube and Super Kamiokande. But what's important, really, for us to bring back is that this horizon here is the end of our current scientific theory. It's the end of our analogy of nature. And this is why I'm putting this slide back up, because there's lots of future scientists in the room. And I want you to understand that, okay, you're going to need to understand the theory to a much more technical degree than I've explained with Lego. But I'm hoping that you guys are going to be the people to basically push this horizon further towards the Big Bang and to help us understand a little bit more about the universe. So that's it. Thank you very much for listening. And if you've got any questions, I'd be very happy to take them. Thank you.